Good morning, students. So once again, welcome back to the online class. So to the continuity of the last class, nonlinear programming algorithm, we discussed a problem related to separable convex programming algorithm. We have seen some example the last class. Now to the continuity of the nonlinear programming algorithm. Now let's move to the next topic. If the objective function is of the quadratic sense. So in that situation, how one can solve? So such a format is called the quadratic nonlinear programming algorithm. So to solve this, we first try to rewrite the quadratic form into the matrix formation. So now let's see a small introduction about the quadratic programming. A quadratic programming which is defined in the form of maximize z, for example, if I consider the objective function, if it is of the form cx plus x transpose dx, subject to the constraint capital Ax less than or equal to b with the x are all positive. So what is this x? Which is nothing but the variables, n number of variables, transpose, and what is c? The coefficients, that is c1, c2 and so on, cn. So how many number of variables? That much number of constant here alone. And the constraint, from the constraint, the b is nothing but b1, b2 and so on, bm. So that is m number of constraints here we are assuming, transpose. So and what is a? This is nothing but from the given objective function, we can observe that the coefficients of the x is like this: a11, a12 and so on, a1n. Similarly a21, a22 and so on, a2n and so on, am1 and so on, amn. So m denotes the number of constraint and n denotes the number of the variables. And what is d? So it is a symmetric matrix, d11, d12 and so on, d1n. Similarly d21, d22 and so on, d2n. Similarly dn1, dn2 and so on, dnn. So now how to solve this objective function? That is one of the technique based on the Karush-Kuntakar technique. So the Karush-Kuntakar technique we are going to apply here. Already we discussed this case also. So now we are going to obtain the necessary condition for the given objective function. So here we are very shortly given the Karush-Kuntakar condition we are going to discuss. So the given objective function can be replaced like this. We can modify it like this, right? So there is no change in the objective function, only the constraint. So here we are take it as a G capital X, which is equal to AI identity matrix minus I, sorry, X minus B0, which is less than or equal to 0. And we are consider here the lambda. It is nothing but the Lagrangian multiplier. And similarly U. So the Lagrangian multiplier lambda 1 and so on up to lambda m, that is that much number of constraint. How many constraint? That much number of Lagrangian multiplier here, transpose. Similarly mu1, mu2, so on, mu n transpose, or the Lagrangian multiplier corresponding to the condition Ax minus b less than or equal to 0. So this is based on this case, and minus x less than or equal to 0. And the Karush-Kuntakar condition is going like this. After making a suitable modification, we observe these the things. So the matrix, it is 2 by 4 matrix. So minus 2D, A transpose minus I, 0, null matrix, that is A null matrix. These entries are zeros, I. And here the variable X, Lagrangian multiplier, and this S. So what is this S? This is nothing but talking about the this S is nothing but here S is equal to B minus AX, which is greater than or equal to 0, nothing but the slack variables of the constraint what we are considering. So on the other side, it is C transpose B, right? So all those things we can discuss with example, but further the Karush-Kuntakar condition is restricting this condition, that is it should be like this, that is the product of the Lagrangian multiplier mu I with the variable xj is equal to 0, which is same as another Lagrangian multiplier lambda I sj is equal to 0. This is true for all I and j, right? And further observation, the Lagrangian multiplier lambda, u, the variable and slack variable are all positive, right? So this is the Karush-Kuntakar condition. So now the given objective function can be rewrite like this. So once we are rewrite it, then how to solve this objective function? That is the next question. So we'll put it in the standard form based on the KKT condition. So solving this like a previous concept what we have discussed, the simplex method. Here we are going on phase 1 of two-phase method, right? So let us see this. What is the meaning? The phase 1 of two-phase method. We are doing example here. So let us consider one example. So here is an example. Solve the quadratic programming algorithm for maximize z 4x1 plus 7x2 minus 2x1 square minus 2x1 x2 minus 2x2 square, subject to the constraint x1 plus x2 2x2 less than or equal to 2, x1 x2 are all greater than or equal to 0. So clearly the objective function here we are looking, it's not like a previous concept that we have discussed, it is clearly in the form of quadratic form. So therefore this can be put it in the standard technique as early in the introduction what we have discussed. So this 4x1 plus 6x2 minus 2x1 square minus 2x1 x2 minus 2x2 square can be rewrite like this. So this is easily one can observe, because if you modify this, that is I am considering these two cases 4x1 plus 6x2, that can be put it like this, the row matrix and column matrix. If you multiply it, this is clearly 4x1 plus 6x2, so you get these terms, right? So and the remaining terms, that is degree 2, that can put it in the separate form. So therefore the remaining terms we can easily put it here. If you simplify this, you will get this one. So for example, instead if you consider like this, so minus 2x1 minus x2, right? Now this is this entry, and multiply with this x1, you will get this form, right? Similarly x1 minus 2x2 multiply with this x2, you will get this, the remaining part. So modify this, it will get back this case, right? Now the constraint can be rewrite like this, that is 1 to x1 x2 less than or equal to 2. So we already from the problem we observe it, it is nothing but x1 plus 2x2 is less than or equal to 0. That is the things we'll put it in the standard matrix form. So already we observe the Karush-Kuntakar condition that format, that is minus 2d, right? See here everything will put it, that is the C, right? And this is nothing but the identity matrix minus I, and these entries are zeros, and here this entry is I, right? So that is the things, everything we put it. So minus 2 into D. So D, just now we observe this case. Right, so these are the things, minus 2D, A transpose A, 0, minus I, 0, 0, I, right? So that is the things, here we will put it. Here we will put it. So minus 2 times D, right? So D is, in this example, this is nothing but our D. So that is the things, here we will put it. And this is A transpose. So A, here we observe it is nothing but the 4, 6, that one here we will put it. Sorry, not 4, 6. This is the A. Sorry, 1, 2 here. So 1, 2 transpose right? So the remaining entry is zeros, and here minus I. So here, what is the order of the D? That much order here we have to assume it as a minus I. So therefore minus 1 0 0 minus 1. So identity matrix multiplied by minus signs. And remaining entries I have to put zeros, and to make it, this is the a proper sense, that is 3 by it is 3 by 6 matrix. So I have to put here the identity value, therefore we take it as a 1. And the next one is what? Here capital X. So here the number of variable, nothing but x1, x2. And the Lagrangian multiplier, here we are consider only one Lagrangian multiplier, lambda 1 and mu1, mu2, right? Because the number of variables, that much number of Lagrangian multiplier here. This lambda 1 reflect the number of constraint what we have. So therefore only one constraint, therefore we use lambda 1, and that is less than or equal to, therefore we use only one slack variable because it is one inequality, right? And the right hand side it is C is nothing but 4 6, right? And the B is what? Nothing but the less than or equal to here from the constraint 2. So that is the things here, right? So after making a suitable modification, taking this minus 2 here and making, this is for only just understanding purpose, I'll put it like this. So this is the standard form after making a suitable modification. So now the thing is, think it about this case. That is, once we will put it in the standard form, then we can go for the phase 1 method. So phase 1 method, before moving to the phase 1 method, the thing is what? I want to form an identity matrix here. So how I will put the variables here? So here x1, x2, the Lagrangian multiplier, mu1, mu2, right? And all these entry here I will paste it. Here I will paste it, right? Now this much, this is, it is nothing but the row is 3, and therefore I have to form 3 by 3 identity matrix here I have to form. So what I have to do? Already slack variable is there, and the remaining two things I have to put. So naturally I have to assume it is a artificial variable. So that is the things in the phase 1 method, right? So this is only one constraint, therefore we use the S1, and the remaining things I have to use it as a artificial variable because I want the 3 by 3 identity matrix. So that is the things reflected here. It is an identity matrix, and we'll put the artificial variable, the first one as R1, R2, then S1, right? So here again the things now move for the solution now. So the solution is this one, that is 4 6 2, that also here in paste it. Now the thing is, one more row I have to introduce, that is denoted by R. So what is this R is means? R is nothing but sum of the artificial variables, simply sum of the artificial variables. So here there are two artificial variables, namely R1 and R2. Just adding these two, 4 plus 2 that is 6, 2 plus 4 that is 6, 1 plus 2 that is 3, minus 1 plus 0 minus 1, 0 minus 1 that is minus 1. So here the thing here, in this case you should not do that operation, only you have to restrict it in this case only, that is in the basic variable only, and the remaining this artificial variable and slack variable, simply you have to take it as a 0. So that is the natural things in the initial table we have to assume it. So this is the phase 1 concept, and here once you come back to here the solution 4 plus 6, that is 10. So only here you have to assume it as a 0 in the initial table only, right? Now as usual in the simplex method, what you are doing, we are taking the theta. So how do you take the theta? So in the simplex table, what we are doing, we are computing Zj, then Zj minus Cj, all those things we are doing, but here not that is the case. So here how we have to choose the pivotal column is, choose among the R the maximum value. So among the R, I have to choose the maximum entry. So here the maximum entry is 6, 6, and the next things are small. So therefore among these two I have to choose one. So you can choose anything, that's not a problem, but I go for the first one, this 6, right? So therefore this is the pivotal column. Now the next one is what? The previously here we will put the basis variable and divide it, right? The same concept here also, right? So that is this 4 divided by this 4. That is the solution, right? 4 divided by 4. Maybe you can put the solution here also, doesn't matter, but I'll put it here. So 4 divided by 4, so that is 1, and 6 by 2, that is here I'll put it 3, and 2 divided by 1, that is 2. Now among these 1, 3 and 2, the 1 is the minimum. Therefore, naturally, this is our pivotal row, right? So not like a previous concept we have discussed in the separable convex programming. So this is entirely different. So therefore, this is what the pivotal element. So naturally, what has to do? I have to make this entry become 1 and the remaining entries become 0. So that is the standard procedure, like a simplex method, right? So whether I have to move for the next table or not. So the question is, I have to proceed to the next table because the condition is I have to make all these entries, the basis variable entries, I have to make all these entries become 0 until that I have to proceed, right? So until that I have to proceed the table. So here, so I have to make this all these entries become 0. So therefore I have to proceed further. I choose the pivotal element. So I have to make this entry become 1 and the remaining entries become 0. So this is the operation next I have to do. So here that is the things. I think you are clear. So what I have to do? I have to divide that by 4, right? So therefore, so this is I have to make this entry 1. So what I have to do? I have to divide this entire row by 4. So 4 by 4, 2 by 4, 1 by 4, minus 1 by 4, 0 by 4, 1 by 4, 0 by 4, 0 by 4. Here 4 by 4, right? And this entry I have to make it as a 0. What I have to do? Here 1. So therefore here 2. So I want to make this entry 0. So what I have to do? I have to multiply this, the new after modification, right? So the new row multiply by minus 2 and add with the R2, so that this entry becomes 0. So similarly, I want to make this entry become 0. What I have to do? Simply the new row multiply by minus 1 and add it with this one, or simply one this new minus this S1 row, right? So that is the things here we'll put it, right? So after making a suitable modification, so everything will be changed. So including this, the artificial and slack variable entries also getting changed, right? So getting changed. Now the thing again as usual, I have to check the R. So what is R? Nothing but summing the artificial variable only. But here only one artificial variable, because the previous from the previous table we observe that the R1 is replaced by X1, right? So R1 is outgoing and X1 is incoming variable. So therefore here this is the only artificial variable. Therefore simply put this all this entry here, right? Now this entry is also you have to put. So only initial table I have to make it 0, but hereafter what I have to do? What are other things reflected here? The artificial variable, that everything submit up and put it in the small r. But here only one artificial variable, therefore just simply put this entry here, right? So here, so that is the things I'll put it. Now again as usual, what I have to do? I have to choose the pivotal column. What I have to do? I have to take the maximum value among this. So here 0, 3, 3 by 2, 1 by 2, minus 1, right? So among these 3 is the maximum. Therefore, I have to choose this my pivotal column, right? So now go for the pivotal row. What I have to do? I just take this entry at the solution 1 divided by this 1 by 2, right? 1 divided by 1 by 2. So 1 divided by 1 by 2. So that is the things, nothing but 2. So 4 divided by 3, that is here. Similarly 1 divided by 3 by 2. So among these, which is the smaller? 2 by 3 is the smaller. Therefore this is the living row, that is the pivotal row. So this is the pivotal element, and in other words this is the incoming variable, and this is S1 is the outgoing variable. So as usual, what I have to do? I have to make this entry become 1 and the remaining entries in the pivotal column I have to make it as a 0, right? So what I have to do? Just divide this by 3 by 2, right? So entire row 3 by 2 I have to divide it. So you'll get the new entries. Then think it about this, making these two entries are zeros. So that is the operation we have to do. So already I recall, because we have to proceed further. because this entry does not get all the entries are zeros, right? So until that I have to proceed for next table. So therefore naturally move for the next table. So here that is the case. So this entries I make it as a 1 and the remaining entries I make it as a 0 with a suitable operation. So we will get this, the new table. Now again as usual I have to think is what? So here in this table what we are observed, S is the slack variable, S1 is replaced by X2, right? That is the things, new things, right? Okay. Now the next one, again I have to fix the R. What is R? Nothing but sum of the artificial variable. Again the artificial variable only one row is there, therefore simply cut and paste here. So I'll paste it here, right? So now again I have to choose the pivotal column. Again among these the 2 is the maximum value, therefore this is the pivotal column, right? So now choose the pivotal row. So pivotal row is nothing but just divide this one, 2 by 3 divided by 1 by 3, right? That is 2 by 2 and 2 by 3 minus 1 by 6, therefore it is negative value, therefore we will omit it. So only we have to consider these two. Among these two the one is the minimum, therefore this is our pivotal row, right? Now again as usual technique I have to make it this is become 1 and the remaining entries are become 0. So I have to proceed further, right? So think it about this. Right. So here I'll make it that entry became 1 and the remaining entries became 0. In other words, this R2 is replaced by the corresponding incoming variable as lambda 1, right? So now think it about this R. So what is R? Nothing but adding the artificial variable. But there is no any artificial variable present here. So naturally there is no artificial variable. Therefore I have to put all the entries are zeros because artificial variable is absent, right? So nothing to be added. So therefore what is the things? So I'll keep it. All the entries are become 0, right? Now I can stop here. No need to move further because this R is getting all the entries are 0. So in other words, the x1 value is nothing but 1 by 3, lambda 1 is 1 and x2 is 5 by 6. So that is the things here we will put it. So these entries we can get back to the substituting in the objective function is it. So in the objective function I'll put x1 equal to 1 by 3 and the place of x2 I'll put the 5 by 6. So simplifying all these value you will get what is z equal to. So z is here after substituting and simplifying it is 4.16, right? So we'll get the optimum value. So I hope you can clear in this example. So similarly, we'll take one more example also. I leave it to you. But the thing is, uh, only thing is here we are considering two constraints. So x1 plus x2 less than or equal to 1 and 2x1 plus 3x2 is less than or equal to 4. So the same things. Only thing is here there are two constraints. So in this case, a slide I just only the slight essence of a problem. So the thing as usual, I can convert the given objective function into the standard form, right? You are all familiar that case. So we'll put it in the standard form, this one, right? Again from the constraint here you will observe. So compared to previous case, there is only one constraint. Now it is a two constraint. Therefore, combinedly we are taking this two constraint. We will put it like this. And by using the KKT, one more thing here we have to observe, maybe in the exam point of view, uh, the question itself talking about check it whether it is concavity. So how do you check the concavity? So concavity is nothing but just taking this D, their determinant, principal minor determinant, I have to check it. We already discussed also, right? So here the thinking about the principal minor determinant of this D. So the first principal minor is -2, that is this entry, and the second principal minor entry is nothing but determinant of this one, that is nothing but 2, that is -2 into -3, minus into minus, -2 -2, that is after simplifying it is 2. So the signs are alternate, therefore we can conclude that This is nothing but negative definite. So what it means? Negative definite. The alternate meaning it is nothing but a concave. So the question here, raise it, check it whether it is a concavity or not. So here we observe it is a concavity. Right, now come back. So using KKT, the standard form minus 2D A transpose A, right? So previously A transpose only a single row, right? So now it is a 2 by 2 matrix because there are two constraints. So that is the things here we are reflecting, right? Next one is what I have to put the minus I. So minus I, it is the based on this order, that one I have to introduce here minus I, that is here we will put it, right? And the remaining entries are all zeros, and naturally the variables x1 x2 here, the Lagrangian multiplier, two constraint, therefore lambda 1 lambda 2 and mu 1 mu 2, that much number of constraint. So S1, S2, because it is the constraints are 2, therefore the slack variables are 2, and here the C transpose, and this is nothing but B. So we'll put it the standard form. Now go for applying the KKT conditions and form the phase one method, right? So as usual, we'll put all those things. We already observed the concept also, right? So artificial variable R1, R2, slack variable S1, S2. So all the entries we'll put it from the uh, this case, right? So all this entry just paste it there, right? So that is the things here we'll paste it, right? So here we'll paste all these entries, right? And R1, R2. So I already told it this is nothing but 4 row. Therefore, I have to form the 4 by 4 identity matrix. So that is the why we introduce R1, R2, S1, S2, the artificial variable and slack variable. So we'll form the identity matrix. So we'll, as usual, we discussed in the last class, last example. So that way we'll put what is R. So R is nothing but what? Sum of the artificial variables. So that is 4 plus 4, 8, 4 plus 6, 10. So all those things we'll put it. So as usual, the initial table I have to take here. It is 0. And we observe this is the maximum value. Therefore, this is the pivotal column. Right now, choose the pivotal row. So you know already 6 by 4, 3 by 6, and 1 by 1, and 4 by 3. So among this, the minimum is nothing but this 1 by 2, right? That is 3 by 6. So therefore this is the minimum, therefore this is the pivotal row. Now as usual we can proceed because not all these entries are getting zeros. They have to proceed further, right? By making this entry become 1 and the remaining entries become 0. So all these operation done it here. In other words, x2 replace the artificial variable r2. Remaining thing is no change, right? So as like a previous example we discussed, that these are the things we have to proceed further. So at the final table, we observe that after making the suitable modification, all these entries became 0. Therefore, we can stop it. And we observe that the values of lambda 1 is nothing but 1, and x1 is 1, and mu 2 is 7, and s2 is 2. So here, we have to observe that only x1 is there. X2 is absent. So what is that meaning? X2 is assumed to be 0. If the variables are absent, then that value is nothing but 0. So therefore, I'll take x1 equal to 1 and x2 equal to 0. Now get back to the objective function. Substitute here, you'll get the maximum value, right? So here put x1 equal to 1 and x2 equal to 0. So all those things, you will get a suitable modification. You will get this value, right? So I'll substitute it. So all these value will get it, right? Maybe you can observe one of the KKT condition, Karush-Kuntakar condition I introduced, right? What is that? Lambda j sj should be equal to mu j sj, right? If I take the first j equal to 1, because here j equal to 1 and 2, because the number of variables are 2, right? So I take j equal to 1, right? So you'll get lambda 1 s1. So lambda 1, just now we observe it is 1, and lambda 2 it is absent in the table, therefore it is 0. So it is lambda 1 into s1, right? S1 is also absent, therefore it is 0. So taking these two products and mu1 x1, mu1 x1, right? Mu1 x1, that is also 0. Similarly, lambda to s2 0, mu2 x2 is also 0. So therefore the Karush-Kuntakar condition does not violate here. So we can justify only for that purpose. We are observing these values. So it's a nice thing to see you back. Just completing this topic, this unit. Now I'll stop here. So is there any clarification? Maybe you can mail to me, or maybe you can contact me. We will discuss more in the class once if you are needed. So I hope you are enjoy the lecture. Maybe in the coming class we can move for the next unit.